Well, we should probably get started. Okay. It's already like 3:08. All right. So it's Friday. So don't forget that there is a quiz today on Blackboard. It will become available at 4 p.m. right after class, and it's due at 11:59 p.m. So you can do it, anytime up until then. And it'll still be there, even after midnight, but it'll be marked late, so you won't get full credit. I don't actually know how much credit I'll give for late quizzes, but probably not very much. All right, do it by the due date instead. Okay, so we're here at the end of week 4. So by now I hope that you have looked at the reading for the week, chapters 12 and 13. And chapter 12 was about collections of structured data, where we look at lists and sets. Okay, so we've looked at lists already in class. We haven't looked at sets yet. And we're not going to use sets a whole lot in the course in the future, but we'll still take a look at them. Okay, I'll probably do that today. And I don't have a whole lot to add to the recursive data types chapter. But I like this idea that maybe I should have done this, and so we'll do some programming today as well, where we'll kind of start with a data type that looks like this. So we'll do something similar, okay? But I realized that there were some slides that Dr. Stewart had for this material, so we can go ahead and kind of skim these slides. We've already sort of looked at this material, so it's pretty much review, but I thought this could be useful. Okay, so let me see if I can get these to work. It's kind of annoying sometimes. Okay, so this is where we're talking about algebraic data types. There's sort of an algebra of data, okay, where you have some base types, okay, like ints and floats and stuff like that. In Pirate, we have string and number and Boolean and whatever else. Okay, and then there are ways of taking existing types and forming new ones. And you can do conjunction and disjunction. These are products and sums, and they correspond to these things in C++. Okay, so this is kind of the essence of structs in C++. And then there's also a thing called a union. It's in C, and so it's also in C++. I don't know how often you've used unions, but they're like this. Okay. Here's where it's gonna glitch out on me. Here we go. Right, I'll skip this. Maybe if it lets me. There we go. Right, so many of the types that we've seen, the compound types we've seen so far, have a pattern that's like this, right? So for example, pairs. I don't know if I showed you, but Pirate has a built-in pair type. Okay, so this is the syntax for doing it. You can say, here's how you construct a pair. You use curly braces, and then, so it's the same syntax for the type of pairs and for values of pairs. So this is actually the syntax for the type of pairs of number and number. Okay, and then if you wanted to construct a value of that type, you would use the same curly braces, but then you'd put an actual number in there, or a number on each side. Okay, and so these actually are built. These are like sort of a primitive thing. It really isn't built into Pirate, as far as I know. So when we looked at that pair type that we made ourselves, it was kind of redundant to do that. All right, but then what about lists? So num list. This is something that we can program with today, but it's basically just a list of numbers. All right, and what's the form of a num list? Well, it's either empty or it's a number and a num list. Okay, it's the same. This is the same thing that we've done with lists. All right. And then, so you can kind of generalize this idea of like and or to give us the general form of algebraic data types, and this is how they appear in Pirate. So you say the name, and then this is all or, you know. So data type is one of these, or one of these, or one of these. And then in each of the constructors, you have some arguments, and that's where and appears. Okay. And so yeah, I'll skip over some of this. Here's some examples though where you can implement these. So here's a num pair data type that has a single constructor that takes two pairs. So this is one way of kind of baking your own pair type that's only for numbers. Okay, you can do a similar thing for num. This is an or type. Okay, we call this either, but num or boolean. So an element of this type is either constructed using this constructor with a number, or this constructor with a boolean. Okay. I'll skip this too. All right, well, let's go ahead and start doing some programming. Sorry, I have some stuff already. What do I want to call this? Okay. Okay, because one of the things that we've already seen some are these polymorphic data types. And so I want to go through a few steps to kind of help us to understand, because I think probably not all of the students understand what's going on there. So how do I want to do this? All right, let's implement some pair types again, like we saw. Okay, like let's say we want to have a type for a pair of like a string and a number. Well, we should probably know how to do that by now. So let's make our own data type for pairs of strings and numbers. Okay, and I'll call it string num. Okay, be one constructor, and I'll just name it this. Of course, it'll have a string and a number. That should be fine. Pirate y. Oops. Poly.r. Okay, so far so good. Okay, and now we could do another one. Let's say we want to have a type where it's a number on the left and a string on the right instead. I'll call that a num string. Okay, num string, number, string, and this is fine as well. All right, and so now from our discussion before, we know that product types it's a commutative thing. So basically, these two types should be equivalent, right? That fundamentally they're not really any different. They just swap the order of the elements. And so you could write a pair of conversion functions to convert between them, right? So I could have string num to num string, and this will take I'll call it Sn. It takes a string num argument and produces a num string. Okay. And what will we do? Well, I'll just use cases. Case is string num, Sn. There's only one case, like that. And then what will I do? Well, I need to construct a num string, and there's only one way to do that. Okay, so this is very straightforward. There wasn't really any room for any creativity here. Okay, and then we could do the inverse function as well. Num string to string num, where you take a num string argument, and it's just the opposite, right? Hopefully I did that right. Not quite. Okay. Okay, and so now you can convert back and forth between these. But then this kind of sucks, because now what if you want to have a pair type for some other types? Maybe a number and number, or Boolean and number. Okay, so I could have all sorts of these things. So many. Really, I could come up with infinitely many of these. Okay, and it gets pretty annoying to do. Bool num, put a Boolean and a number. All right, and so this is where the polymorphism comes in. Okay, the type parameters that we've seen already. I can say, well, all these types, they're kind of the same thing. They're very similar. They differ in a few places. And so you can kind of generalize the definition of all these types to say, well, what do they all have in common? And this is where I've already showed you the pair type. I'll say, okay, we can actually make a pair type that's totally general and generalizes all of these by using type parameters. Okay, so this is going to be a polymorphic type for pairs. And what do we do? Well, it's going to be the same as all the others, where we just have a single constructor. But then we'll say the thing on the left should just be a type A, and the thing on the right should be a type B, whatever A and B are. But we don't need to know what they are. These are not actual concrete types. These are type parameters. It's sort of like when you write a function, and the function has an argument. You don't know what the value is going to be because, well, it depends on how the function's used. People can call in different, passing in different values for the argument. And it's the same thing here. This is not actually defining a single concrete type. This is actually, we're defining a family of types. This is like a schema for pair types. Okay, so let me finish the definition. I guess I could call it A. Okay, so now once we have this defined, we could do something like pair of number string. And now that's a type, okay? Where you take some concrete types and substitute them in for the type parameters. And so now what does the constructor for this type look like? Well, it does this. It looks like this because, well, we've said, all right, A is number. And so substitute in number for A. And B is string, and so substitute in string for B. All right? And so, yeah, so this pair type, I sometimes will call it, loosely speaking, I say, well, this is the pair type. But it's sort of not actually a type by itself. It really is like a type schema. It's like a family of types where this is one of them. Okay, pair, string, Boolean is a type. Okay, and you can put in anything here. All right. So this is the idea of polymorphism. Technically, it's called parametric polymorphism. So if you look at the schedule, if you look at the very end, there's some stuff there about parametric polymorphism. So we might talk about this more at the end of the semester. I'm not sure exactly, what we're going to do there. That's pretty far away. But so that just means right now, I really only want to give you the intuition that you need to be able to work with these polymorphic definitions. Okay? So that not only can types be polymorphic, but so can functions. Because now, suppose you want to write a function. We did this before for swapping the elements of a pair. It's like, well, if you think about what the swap function does, it's just taking the elements and swapping them. So it really shouldn't have to care what the concrete types are. Swap doesn't care what the types are. And so it, too, can be totally polymorphic. So we can put the type parameters there. Whoops. Say, oh, okay, it takes a pair of type pair AB and gives you a pair BA. It swaps the order. it will just do this. Something is not right. Line 32. Oh, it's because I left these in. Okay. So again, in a way, the way you can think of this is that we're not defining a single function here. We're actually defining a family of functions, where there's a function called swap for any choices of the two type parameters. So, swap number string is a function that will take a pair of number string and turn it into a pair of string number. All right? So these are very useful. This polymorphic stuff is very useful for writing kind of general reusable code. All right. Okay, and so that's why in the book they have this type for list of numbers that they call numList. So you start with like numList. So we can do this as well. We can roll our own type for list of numbers if we want. And I'll just call it NL empty for the empty list, and NL link for a link, and what goes in the link, a number, and the rest of the num list. So number, something like that. Okay. But again, we run into the same issue here where, well, you need to have a different type for all of your different kinds of lists. So you'd have like a bool list and a string list, and it'd be pretty stupid because then you have to write like a different length function for each one. You have num list length and bool list length and so on. And well, the length function is one of those functions that doesn't really care about the elements. It's just counting how many there are. So that's why in practice we don't use types like this. We just use a single list type. I could call polylist. Okay, but it has a type parameter because it's polymorphic. And the element inside has that type. And the rest of the list is a polylist of the same type. All right? And this is exactly the type the list type in the standard library, except I've called it polylist. But the list type is exactly this. All right, and so then, you can write your length function like polylength in a generic way, so that it'll work no matter what concrete type is chosen for A. And we've seen that, but I'll do it again. Just to show you, just to remind you, polylist L empty, the length of the empty list is 0, and polylink, don't care what the value is, 1 plus recursive call. Oh, compilation error.
Poly empty.
Oh, I see. Yeah. So yeah, I hope that you're I'm going fast because by now you should be pretty comfortable with this length function. I mean, I think you implemented this yourself in the last homework assignment. Right. Yeah. And then, of course, the other notable thing about the list type is that it's recursive. And that's what one of the chapters for this week is about. Which, that's an interesting thing, that our types can be recursive. They can be polymorphic, and they can be recursive. So this is the general setup to, very powerful kind of data type setup where you have algebraic data types that are polymorphic and recursive. Yeah?
So the length thing for the list is not actually a function, it's just a data type?
The length for list?
For a normal list.
For normal list,
It's just a data type function. Because I thought it was a function that adds the element to the list.
Length or link?
Link.
Link is a constructor. So it's like a function, but it doesn't do any computing. But you're right, it does just add an element to the front of a list, because there are two ways to construct a list, because list has two constructors. Let's bring it up. Pirate.
Yeah, for that one, the poly link you put is just it's more of a data type.
Well, the type is polylist of A, or at A, and then it has two constructors, and one of them is polylink. So polylink, it's part of the type, in the data type definition is where you say what the constructors are.
Yeah.
So that's, we're defining the constructor when we're defining the type. But later on, it sort of acts like a function. It's a constructor for the type. And it can appear in the patterns when you do cases as well. But so if you want to construct a value of this type, we can do that. Okay. One of them would obviously be the empty one. I could print poly empty, and let's put a new line here so that it prints nicely. Okay, it printed poly empty. But now suppose we want to have a non-empty list. What would I do? Well, I'll say polylink, and then give it an element. Sorry if that's too low. There we go. I'll give it an element. Say I want it to be a number, and then for the rest of the list I'll use empty so that it will only have one element. And how does it print out? Well, it just prints this out. Right? Like this is the value. So even though it looks like a function call and you treat it kind of like a function, it might actually be a first-class thing, because next week we'll start talking about higher order functions where you can pass functions around as arguments, and if Pirate's any good, then you could actually pass constructors around as if they're functions. Because normally you can do that, but then what do they do when you apply the function to its arguments? Well, it just kind of sits there and it says, okay, I'm a value now of our list type. Right? And so then if you use cases on this, well, it's pretty straightforward to see what the constructor is on the outside, on the outermost level, so that when you do cases, it can tell, oh, this is a link. Right? Okay. What time is it? Whoops. All right. So I don't know. we can look at sets still. What else do we have? Sets are a little funny in Pirate. Oh yeah, well, so don't forget about counting elements of a type. That's still something that you need to know, and especially for algebraic data types. And we saw, I showed you already how it's pretty straightforward in simple cases. Like, suppose we had a pair of Boolean, or, well, how do I want to do this? Essentially, you treat the bars, which they're like or, you treat them like addition, okay? And then wherever there's and, you treat that like multiplication. So you can easily compute the number of possible elements of a type by just doing a little bit of arithmetic. Okay? The only time that doesn't work is when it's a recursive type. All right? So we can look at an example here. I'll just call it my type. And we'll give it some constructors. Okay? my type constructor, I'll just con 1, and say it takes, a Boolean, I'll just make it 3 Booleans. And my type con 2 takes, I don't know, is there a unit type built in? Perhaps not. Here. Should have come up with these ahead of time. I'll do this. Will this work? Sorry. Okay. All right, so now my question is to you. So how many elements of this type are there?
My type 1 or my type?
My type 1. Right. There are 2 elements because there are 2 constructors and they don't take any arguments. Okay? So those are the only 2 values of my type 1. Okay? So that one's really pretty trivial. And the way that you would do that is say, well, you interpret this bar as plus. And, well, there's the extra bar here. So maybe you put a 0 at the top. So, but it's just going to be 1 plus 1. Okay? But what about this one? It's much more complicated. Maybe I made it too complicated. I don't know. But maybe I made it not complicated enough. Go ahead.
Should be 12, right?
Should it be 12?
You've got 3 different booleans on the top. Each can have 2 values, so you get 2. Is that? For me, that's 6. And then on the bottom, you get 4. So that would be cached. But I was thinking you would have 2 to the 3 combinations.
Yeah.
For both, or for the top one, and then
Sure.
2 to the 2 combinations. The bottom one would be 12.
Yeah, so if we interpret the bar as plus and the comma as times, because this is like or and this is like and, then what we would end up here with is the number of elements here times the number of elements here times the number of elements here. So that's 2 times 2 times 2. And then we've got the bar, and it's going to be 2 times 2. Maybe I should have chosen, maybe given this one more constructors or something. We could do that. Just to, so that it's not all 2's. Okay, so now this will be 2 times 3, right? So this is 2 to the power of 3, which is 8. You were right. And then this will be 6 now, because I've changed it. Okay, so that's like 14, right? 8 plus 6 equals 14. I hope I can do math. So that's the total number of elements of this type. All right. Call my type 2. There. Make sure what did I do wrong? Oh. Okay. All right. Well, let's try another type. My type 3. And I'll make it kind of the same. Perhaps I'll get rid of one of these and make this a number. Type checks.
But doesn't this get to infinity the moment you add the number?
Huh?
Doesn't this get to infinity the moment you add the number to an infinite amount of numbers?
Yeah, it does. So that's the answer for this one. The number of elements of this type is that there are infinitely many. Right? That's how many because there are infinitely many numbers, as far as I know, because the numbers include arbitrary precision rationals. Okay, so that wouldn't be the case. Like if this was your C++ int type or something, then it would be finite, because the int type is the type of fixed size machine words, bit patterns of 32 bits or 64 or whatever, and so there's 2 to the 32 or 2 to the 64 possible values there. But here we actually are using, I believe that Pirate uses sort of big numbers, okay, that can be any size, as long as we don't run out of memory. So you're right, infinitely many. Okay, and now we can revisit one of our types here, like our poly list. How many values of, well, again, if I just ask you how many values of this type are there, it would be kind of an ill-formed question, because this by itself isn't really a type. I would have to choose something for A. Then it would be a type. Okay, so let's say I have poly list of bool. Boolean. Okay. How many values of this type are there?
It depends on the number of elements on the list. Because it's 2 times the 2 to the power of the number of elements in the list.
Well, how many elements could there be? Yeah. Yeah, so let's look at some example values of this type. Okay. Polyempty is one. Okay, so we've already seen some of these. Polylink, how about false and then polyempty? That's one. You could have polylink true, polyempty. Okay, but then you could keep going with this. Well, these are values, okay, of the type, and well, because it's recursive for the rest of the list, we could keep kind of adding on more and more, and we would never get to a point where we've exhausted all the lists. There are infinitely many, right? So that will be true under most circumstances. When you have a recursive type, it will have infinitely many elements. But that's not always the case. There are some situations, some conditions under which this type won't have infinitely many elements. And we've seen one of them. All right. So what would one of them be? If we left this out. Suppose we left out the empty constructor. I'll just get rid of it. Okay. And so, we looked at this last time, I think, or at some point, where we were trying to find a way to construct a value. We were looking for an example value of this type. And if you try to do that, it's very difficult, because we don't have this polyempty thing anymore to end the list. And so you just keep going with polylinks, and you'll never end. Okay? And so there is no element of this type. So yeah, you'll find with recursive types, pretty much there are either infinitely many elements or none at all. Now that's not the only time, though. It's not the only time that can happen. Okay, let's add the empty constructor back. But if you remember, there was a type before we looked at. I'll redefine it here. I called it 0. And what was the weird thing about 0? Well, that it had no constructors at all. So it's an empty type. Okay. And so now, my question to you: how many elements are there of this type? Poly list of 0. Yeah?
Just one. Yeah.
Sure. Yeah. I believe that's right. So, right, polyempty is always a list. But then, what if you try to construct something other than polyempty? You'd use polylink, and then you have to put something of type 0 for the argument. What do you put there? There is no element of type 0. Okay? Now, that isn't to say that you couldn't... there's no value of type 0. So you could come up with programs that would type check that might look like you'll have a non-empty list of type 0, but they would just diverge. They would loop forever. You could come up with infinite loops of any type. You can always do that. Watch this. Make 0. 0. Comment these out. Okay. So now here, if there's anywhere, if there's any context that expects something of type 0, you could put this there, and the type checker would be satisfied. So I could say print. Maybe I shouldn't do this, but polylink make 0 empty poly empty. Okay, and this will get past the type checker, but then it's just going to loop forever. So there are always these kind of degenerate cases when your programming language allows for infinite loops. Then you can do that. But there are no values. So any like well-behaved program, one that terminates, you can never have a value of type. You can never have a non-empty list of type 0. Okay. Okay. So I guess with the remaining time, we can look at the set type. The set type. So let me find in here. So they talk about lists a bit, and then we get to sets. Right. So sets are good for when you don't care about the order and you don't care about duplicates. Especially if you would rather there not be duplicates. And they give some examples of things. Okay. And eventually we are going to get to a point where we're kind of implementing these sets ourselves. And so there are a couple weird things about sets. One of them is that there are actually two different kinds of sets in Pirate. I don't know if it mentions this here in the textbook, but if you go to the documentation for sets, then you'll find right away they start talking about this. So there are two underlying representations that sets may have. We have list-based sets. Okay, so that's where the underlying implementation is using lists for the storage. They do talk about this a bit in the book. And then there are also tree-based sets, and they have some different requirements. Okay, if you want to use a tree-based set, then the element type has to be an ordered type. There has to be a less than method defined on it. However that is done, I'm not sure, but you could do this with numbers and strings probably, and Boolean. I presume that the order is defined on them in the usual way. And so, we have this notation for constructing sets that's very similar to what you can do with lists. Okay, but you say list set if you want a set that's backed by list, and you'll say tree set if you want a set that's backed by a binary search tree. But, and if you just say set, it defaults to list set. So you can just say set instead. So that's one of the weird things about sets. And the other one is this pick thing, sort of how you do computation with a set. And I suppose we can look at it here. So what is this function doing? It says an element, short for element. So it'll take a set. Of course, they're not using types. That kind of bugs me, because I believe the set type really is, where is it? Right? It's polymorphic. Okay? And it has a type parameter there. So you should really pretend that that's here. That this should be a polymorphic function where there's a type parameter, and then that parameter appears there as well. And of course, they also left out the return type. It should be returning an element of that type. So, let's write this ourselves. Let's write a better version. Okay. Let's see if this type checks. Probably not. Okay, well, to use pick, they're using this pick thing. I think you have to include that. And I don't know, do you need includes at the top? Whoops. Error is unbound. Okay, maybe the code in the book doesn't always work as is. Okay. Okay. Yeah, so if you're using the type checker, then you'll see an error here where it says, well, set expected a type argument. Because it's a polymorphic type. So let's make this better. Like this. Say, okay, this function is generic in A, and it takes a set of A, and it's going to return an A. Now, will this work? Looks like it does. Oh, is it still looping forever? Where did I do that? Yeah. Oops. Okay. All right, so now we can look at what this is doing. You can guess from the name, it's an element. So it takes a set and just pulls an element out of the set. But it does it using this pick thing, okay? Because they're really, they emphasize this idea that the set doesn't guarantee any ordering. So when you pull, there's no such thing as pulling out the head of the set or the first element. There is no first element. All right? And so you use this pick method on the set. And what pick does is it produces a pick value where there's a data type called pick in the standard library that looks like this. Okay? It actually has two type parameters and two constructors. So an element of a pick type is either none. That's what you would get if you tried to, pick from an empty set. Or it's pick sum, where this will have an element of the type and another element of the type B. So we're in the set thing. Here's the pick method on sets. Okay, it doesn't take any arguments, so you just call it with parens like that, and then what does it give you back? Something of this type, where it's pick of A on the left and set of A on the right. So let's look at our type again. So we're saying A will be the type of elements in the set, and B is set of A. Okay? So the way that it's being used, when you call the pick method on a set, well, it gives you an element and then the rest of the set. Okay, but it's going to be in no particular order. So you end up doing it. This pattern is just like processing a list, except you don't know what order you're going through the set in. Okay. So this is very much like what we've done with lists. You do cases, but then instead of doing cases on the set itself, you're doing cases on a pick value that you got from calling the pick method on the set. And then there are two possibilities. It could be none if the set was empty. That's what would happen. And then we'd say, okay, this is an error because we're trying to pull an element out of an empty set. Or it can be pick sum with the element and the rest of the set, which is the original set with that element removed. Of course, it's not being used here. But suppose we wanted to, print elements. I guess I could do this. Or, yeah, that'll work. We'll take a set. And, oh, can you do this? Sorry, I don't remember. It doesn't like that. 109, yeah. I don't know if there's the unit type or something. Maybe I just leave it out. Okay, please annotate its return type. Huh, I wonder, it's not going to like this. I could introduce my own unit type. Well, let's try to write the body first. We have time, right? Okay. So all we want to do is just iterate through the set recursively and print all of the elements. So we'll do this thing where we pick an element. If it's none, then I want to do nothing. Yeah, I don't know if Pirate has a unit type. Let me make one. Data unit TT. Okay, so then it's like if I don't actually want to do anything, I'll just return the unit value.
Is there no way to break from the function?
I don't think there is, and that would be. We don't really like doing that in general because basically in functional programming, you want your functions to really be functions. And one of the things about functions, like in the mathematical sense, is that they're defined on all the inputs. Okay, you can call that a total function, but we really like when our functions are total in that way. So if there were like this is not a total function technically because it can raise an error, but we want to minimize that as much as possible. Okay, so if there were some inputs that we didn't like, it's better to actually be able to produce something of the return type, and so we might get to some of this later on when we get into some more programming techniques, where instead of raising errors like this, you actually just have a return type that like one of the constructors of the return type is for an error. And that way, what would you do in the error case? Well, you just return, you're still returning a value of the return type, but it's one that signals an error. Time? Okay, yeah, we're running out of time. But, I suppose I don't really have time to finish this. But in this case, we would say pick sum, and then we would print out the element and do the recursive call on the rest. All right, now, we might have a quiz. And don't forget the quiz on Blackboard today. All right, let's find out. Wow, you're lucky. All right, see you next week.